All right, hello again. Does everyone hear me?
Yes.
I hope. Okay, I hope my internet connection is not gonna fail me because I'm not in campus anymore today. All right, so let's get started with another chapter. I'm gonna share the screen with you. So this is chapter 8. We're gonna learn about evolutionary algorithm or evolutionary solver. You're not gonna see an algorithm there. It just says that evolutionary solver, and it's going to be in Excel. It has been added recently. By recently, I mean probably the past less than 10 years ago, like 6 or 7 years ago, it has been added. But before that, the evolutionary algorithm, it has been used for more than 20 years, as far as I remember. And those are genetic algorithm, simulated annealing, particle swarm, ant colony, network, neural network, and some other algorithms. Okay, so let's see. This is chapter 8, by the way. So chapter 8 describes a fairly new alternative optimization routine called the evolutionary solver. So you're going to see it as everything, the menu is it's going to be the same. The windows are going to be the same thing that we use for solving any optimization so far. It's going to be on the solver, but it's just if you remember the choice that we had to pick the solver, here we're going to use the evolutionary solver, which is another option there. So we're going to use that. So you're not going to see what's behind that window, but that's what it does. It's going to use one of those algorithms. Probably it's going to use genetic algorithm. So we're not going to get into deep into genetic algorithm or other algorithms that we're going to use, but these kind of algorithms are suitable more for problems that are not easy to solve with the classical approach, the mathematical optimization approach, such as the simplex algorithm, the MIP approach, branch and non-branch and cut, etc., etc. Because they could have, like here, we're gonna see in the model in Excel, we're gonna see like non-smooth modeling or discontinuous, or using some functions in the modeling, such as if, index, countif, lookup, the absolute value, mean, max, round, integer. So you're gonna see examples of these today in this lecture. We're gonna solve actually 3 important algorithm or problems. The most popular one is the traveling salesman problem. The TSP is called. It's one of the most popular classical optimization problem that is still used today. Like any logistic company is actually kind of sort of using this type of algorithm or problem to solve it's one of the challenges to solve TSP. For example, Amazon, the food delivery companies, Uber, Lyft, USB, USPS, so on and so forth. The next problem is the discriminant analysis, and also we're gonna solve another problem, which is kind of sound familiar to me. It's the forming project teams for, say, for a class that I'm going to give you. So this is a max-min problem. We could have a min-max problem. That means you are minimizing the maximum of something, or you're maximizing the minimum of something. So as you see, this is like discontinuous, non-smooth, non-classical type of problems. So let's start a little bit, go into more detail about the evolutionary solver, particularly the genetic algorithm. So the genetic algorithm, or GA, it kind of uses the concept from biology. So we don't have objective function. We have objective function, but we call it the fitness function as the evolutionary biology goes. We call the solution chromosome. And we have a set of niche solution that we call them the population. So the approach, the genetic algorithm approach is you have a pool or a population of solution or chromosomes that you're gonna generate new population or generate new solution by two methods. One is called the mutation, and that again comes from biology, and that's actually getting a chromosome or a solution and changing randomly, mutate the chromosome. Okay, that would translate into changing a solution randomly. Or we could have the next thing that goes in biology evolution, and that's actually mating. So, for example, two solution or two parents, a father and a mother, they're gonna mate up and they're gonna have an offspring, which is a new solution. So this is called crossover, which is combining two solutions to get a new or a couple of solutions. So as you see here, or might have noticed, it's very cool. And the best thing is about it is it actually works. So it cannot guarantee, any of these evolutionary algorithm cannot actually guarantee you an optimal solution, but they will be able to give you a good solution very fast. So you don't know the solution that you have is optimal or not. You don't know when actually to stop. So you have to put a stopping criteria. So that's what kind of make it kind of challenging. So the strengths of these evolutionary solution methodology, or as we call it, heuristics or meta-heuristics. They can handle complex models with unusual functions and unusual models that cannot be solved by classical mathematical optimization methods. They tend to find a good solution very fast. And the drawbacks, as I said, you don't know when to stop, so you have to come up with a termination criteria or stopping criteria yourself. For example, how many new generation you have to produce, or it could be timing, it could be improvement from the initial best solution. So in any generation that you have a population of solution, there is a best solution. You can start with the first population and generate new generation. So your best solution is going to improve. So you can actually, one of the criteria is you can actually set a percentage of improvement based on your initial best solution that you have. So that could be another termination criteria, stopping criteria. Also, again, you don't know whether you have an optimal solution in hand or not. So that's also a drawback. And there is also a drawback in what is called that tuning the algorithm. And that's because the algorithm is going to have certain parameters that you need to figure out what value you should pick for them. For example, a population, that means a certain number of chromosomes or certain number of solutions. So how many solutions you need to have? Is it 100? Is it 100,000? Is it a million? So that's a value that you have to find the value for. And it's going to make change. So it's going to impact your algorithm, it's going to impact your timing, so timing of finding a solution. Also, it's going to consume memory and computation power. Also, how do you define crossovers, the mating or mutation? Again, a stopping criteria, right? So you have to kind of tune or think about these parameters as well. So that's one of drawbacks. We're going to start off with the most popular problem that you're going to solve here. So we're going to start off with the traveling salesman problem, or TSP. What is the traveling salesman problem? So it's actually very easy, although it's very difficult to solve because it's called the combinatory optimization problem, and it's not a classical linear programming that you can solve it using simplex algorithm. So this is how it goes. A salesperson wants to visit customers in N cities, say in the United States. pick N cities, say 50 cities in the United States in different different states. So these different cities, they're going to have different distances to each other. And what the salesperson want to do is to actually visit all of these cities only once, and then comes back to his or her original city. So it's gonna go travel and get a route all over all those cities, visit them once. And what the objective here is to minimize the total distance traveled for the salesperson. So that's a problem that can can be is challenging to Amazon deliveries, for food deliveries, for Uber Eats, for Uber, for Lyft, for UPS, etc. So on and so forth. So that's the problem. What is the shortest or fastest, least expensive route that goes through all of the N cities and visit them only once and then return to the start? And to give you an idea how difficult this problem is, if you have N cities, the number of possibilities or total number of routes possible is N factorial. And in fact, N factorial can get hugely big. For example, for just 14 cities, the 14 factorial is more than 87 billion routes. So you can see that if you just want to generate all of these 87 billion possible routes and then compute all of the distances for them and then pick up the best one, that's going to be crazy, right? So that's why how important it is to have an effective method to solve this problem, or give you actually a good, not necessarily the best solution, but give you we hope to find the best solution, but sometimes we cannot afford to do that because the problem is super hard. Okay? So I'm going to talk about this later on. Let's go to the example. So we're going to visit actually the same problem that we already have visited kind of a couple of weeks ago. The Western Airline Hub. We have added 2 more cities, the Minneapolis and St. Louis in Missouri. So these are the 40 cities, location in the United States. As you see here, we have Boston, New York City, Pittsburgh, Chicago, St. Louis, Atlanta, New Orleans, Houston, Denver, Salt Lake City, Minneapolis, Seattle, San Francisco, and LA. So the total possibilities again is 14 factorial, which is more than 87 billion. This is just an example, not, of course, it's not all of the routes, but you can see that kind of give you an idea how you can approach it. For example, you can go start from LA, then go to San Francisco, then Seattle, then Salt Lake City, then Denver, then Minneapolis, then Chicago. From Chicago, should you go to Pittsburgh or should you go to St. Louis, right? So there are a lot of actually possibilities here. What you're looking for is the best route or a good route. Here we're going to actually find the best route. All right, so we can formulate this problem in a mathematical format, like the classical mathematical optimization format with formulas. But here we're going to use Excel, which is actually, compared to the mathematical optimization model, mathematical formulation is actually much simpler and easier to understand. And also, if you can look at this problem, it's kind of being, say you have 14 cities, okay? So if you just name these cities by number, finding the best solution is finding the total possibilities actually, or the factorial here is the total permutation for all of these cities together. For example, if you make if you consider a city a book and you want to put these books in one shelf, and the first book actually is this first city that you visit, the next book is the second city that you visit, and so on and so forth. The total possibilities that you can actually arrange these books on a shelf is similar to what we want to solve here, to find the best combination of putting these books together or visiting these cities so that we minimize the total distance visited or travel. One of the good things about the evaluation solution that we have in Solver in Excel is it gives us actually a kind of constraint that we didn't have before, and we're going to see it is called the all different. That means that you want to pick different cities. So you want to pick 14 cities, but each city has to be different. That means that you have like 14 position on the shelf. Going back to the example of books, then you want all these positions to be filled with different books. That means you're arranging books. So you because you only have, say, one Chicago, you cannot put Chicago first and say in the middle, right? So that's why you want to have it all different. So that's one of the powerful constraints that we have in Excel for the evolutionary subgroup. And also we can actually use other functionality of Excel, such as the index and the sum product, etc. So we're gonna use those to make our modeling and our life easier. Again, the objective is to minimize the total route distance for going from the first cities, visiting all of the cities once, and then coming back to the starting point. Okay, so we want to minimize the total travel distance. Okay, let me go back to open up actually the Excel file. So I'm going to open the data, TSP data file. You can actually download the TSP data file and follow along as I try to solve it here. So let me share this with you. So this is the data in Excel. We have 14 cities. These are the abbreviation of the city: Atlanta, Boston, Chicago, Denver, so on and so forth. This is the matrix called the distance matrix. So I'm going to name actually this similar to what we had before. I'm going to come back here and say distance matrix. I'm also going to create actually label these cities by numbers. 1, 2, 3. I'm going to drag this down to make all of these cities have a label. So Atlanta has a label of 1, Boston has a label of 2, Chicago has a label of 3, and so on and so forth. All right. What else do we need? So again, this matrix actually is symmetrical. That means that you know, the distance between, because this is travel distance or air distance. That's why the air distance between A and B is similar to B and A. So that's why the Atlanta to Boston distance is 1,000 miles, and to Boston to Atlanta is the same. So that's why we have symmetrical. The upper triangle and the lower triangle are actually the same. And every distance, every city's distance to itself, of course, is 0. That's why you see zeros on the diagonal here. Okay, so what we need to do, these are all our inputs. So that's why we use the input style here, the bluish color. So I'm going to create some calculation here and also our decision variables. For example, I'm going to create the decision variable. That's our decision is actually the route that we want to traverse. I'm going to call it route, and this is going to be our route. My decision variable. So for example, if I have 1, 3, 4, 6, 5, 7, 9, 8, 11, 10, 14, 13, 12. What did I not use? 1, 2, 2. Okay, 2. So this is one possibility here. So to make it easier actually for us to read it, I'm going to name the cities here. Names. This is just to give us kind of moving back to what this was. Yeah, absolutely. So for example, 3 here is Denver. 4 is LA. Well, this is not right. I'm gonna do that later. All right, moving back to our decision. So this is the route. It starts say from 1, which is Atlanta, then goes to 3, which is Chicago, and then goes to 4, 6, 5, 7, 8, 9, 10. And the last thing is it has to come back. Okay, so we have 14 actually variables here, but because it's going to also come back, we're not going to count that one as a new part of our decision variables. So I'm going to add it here without using the theme or format here. So this is going to be, again, the first cell, whatever it is. Right now is 1. If I change it to whatever other values, it's going to be reflected here. Okay? This is because any route has to start from a city. It has to come back to the city. This makes sure that the route comes back to that city. So what we want to do is we actually want to find the distance for this route. Okay, so for example, the distance is going to start from CD1, then going to go to CD3. So CD3, we have to find the distance from CD1 to 3, which is from Atlanta to Chicago. Okay, so I'm going to write here distance. So for that, what it has to do is it has to take this matrix, the distance matrix, and then it has to find this city and this city, and then find from the distance that it is here. For example, it's gonna say from 1, which is Atlanta, to 3, which is Chicago. So it's gonna say 674. So this is index. This is row. The distance from this city to this city. So that's 674. Let's just check if this is correct actually. So from city 1, which is Atlanta, to Chicago is actually 774. So this is correct. I'm going to drag this actually down here. So you make sure that it's correct. So from 3 to 4, it's 1008. That means from Chicago to 4, which is Denver. Chicago to Denver, 1008. So this is correct. Coming back from 2 to 1, 2 to 1, that's Boston to Atlanta, which is 1037. So it looks like actually our distance is correct. Now that we have our distance, if we actually add up these, it's going to give us the total distance traveled. By the way, let me actually reiterate why we added 1 here, which is the first city, starting point. This is because I use the index here to find the distance from this city and the next city. So this city is 2. It's going to go back to the starting point city, which is 1. So that's why I have to add 1 here. Okay, just for modeling purposes and make the route, ensuring that the route comes back to the starting point. So we can actually create our total distance or objective function, the total distance traveled here. So I'm going to call it total distance travel. Total distance travel. And that's going to be just the summation of these. So right now is 19,166 miles. I'm going to, because this is our output, I'm going to use the output style here. I'm going to also name this for the sake of model. I'm going to name that one as well. Let's see. So I'm going to name it. All right. So it looks like that it worked. What else do we need? So we had the inputs, the decision variable, and the total distance, which is our objective function. I think it's ready for us to solve the problem. Let me go to solver here. So here we're going to, so as you see here, we're going to use the same solver that we used before. It's just the solution methodology that's going to change. I'm going to show you later how we can pick that. So set the objective is going to be in this cell. We want to minimize it, and our decision variables are this route. I'm not gonna include the last one. That's because that's our starting point. So we don't need that because it's always going to be there. And then we're gonna add the constraints here. So what are the constraints? So first of all, these values has to be all different. So I'm going to pick all different. See, this is what it says, all different. Okay. I'm going to add that one. Okay. So that's what we had. What else do we need? I think that's it. So let's go back here. Here, I'm going to use the evolutionary algorithm. We're going to have to visit the options here because there are certain parameters that need to check. So first of all, the algorithm doesn't have a stopping criteria or termination criteria. So we need to add that. Here you can use the stopping criteria as time here. For example, 60 seconds at 1 minute. I'm gonna see if 13 seconds work to just make it resolve fast. That means it reached the time criteria, the stopping time criteria. but it doesn't know whether it has reached the optimal solution or not. And that's one of the problem. So you have to decide whether you want to continue or stop. I have solved this before, and actually they on the same. I have got the same value. So I'm gonna click stop here. So it says the solver has found a solution. We don't know that this is the optimal solution or not. So that's one of the drawbacks here. But this is what the solution looks like. You might actually get different route here. That means it could be not necessarily the same. But I think if you're gonna run it for say 3 minutes or 4 minutes, you're gonna have probably the same total distance. So the total distance that you might get probably is going to be the same, but not the route. The route might actually be different. But what we care about actually is the total distance. So that's our goal. All right. Any question?
So, Professor, the each route that comes up, whether it's different from yours or not, they're all technically correct because they all are the same distance. Is that right?
Yeah, that's what we care about. We don't care about the cities. You know, what city we should visit next. What we care about is we want a route that would minimize our total distance travel, right? We don't care, you know, whether we have to start from any city and you know what city we should visit next. That could be another different problem. If you care about what cities you should visit, that's going to be should be included in your constraints. But right now for this problem, we don't care what cities we start, what cities we actually next go to. What we care about is the total cost of traveling, which is the total distance. So we want to minimize that. So you might actually, I mean, if I actually run this problem again, probably I'm going to get a different route here, but the travel is going to be, the total distance is going to be the same.
Okay, thank you.
Sure. Let me see if I can actually get this correct, because right now it's like it's just a number. So I'm gonna pick these. The row here is going to go for that's 19. Oh yeah, it works. So 14 is actually what is it? The St. Louis. So if I drag this down here, it worked for New Orleans. 7 is New Orleans. No, it didn't. What is wrong here? Okay, I have to actually use absolute cell here to make it work. Let me try it again. Okay, let me go here. So 5, it says it's Houston. Yes, it's Houston. LA is 6. LA is 6. Right. So now we know the route. It says that to start from St. Louis, then go to Minneapolis, Seattle, then San Francisco, LA, Salt Lake City, then Denver, then Houston, then New Orleans, then Atlanta, then Boston, then New York, then Pittsburgh, then Chicago, and then go back to the Salt Lake, the St. Louis. And the total travel is 7,695 miles. So if I just give it a random, so the random one is 16,000, but our optimal solution or our solution that the evolution algorithm was 7,000. 7,600. All right. Any question? Let me go back to slide, see what we had there. Okay, next slide. So this is a map that shows the perfect route trip. Has been on this actually link, which is the smart news link. So probably this is the like 50 top US tourist city attraction cities. And the route that you see is probably the shortest path, or the optimal TSP, travel salesman problems. As you see here, could start from any of them, then travel along these links or routes, and then to that city, and you would have traveled the least total distance. Okay? Using actually solver, depending on your computer power, of course, you can actually use the solver to solve larger problem that we solved here. We only had 14, and 14 was more than 87 billion possibilities. So you can easily, not easily, but you can actually solve a TSP with n equal to 100 using Excel. Just it's going to take a couple of minutes, depending on your computer. RAM is important also. The processing power is also important. So you might be wondering, what would be the largest TSP problem that has been solved? So there is actually an article here. There might be another advanced one or an update, which is a larger problem that has been solved, but there is an actual article from 2009. They have proved that they have solved a TSP problem for 85,900 cities. So just imagine if 14 cities has more than 87 billion possibilities. Imagine what would be the total possibilities for almost 86,000 cities. It would be like galaxy distance. All right. So that's our first part of lecture. We are done with the TSP problem. Any problem, any question, any comment? I'm gonna move to the next problem. The next problem. Close up the TSP envelope here. Part of the chapter, part 2. We're gonna solve another problem that you can solve using the evolutionary algorithm, evolution solver. It's called the discriminant analysis. This is a type of problem that, compared to what we have solved before, it's very interesting. It's actually more close to classification type algorithm, supervised learning. In machine learning, you might have heard about the buzzwords machine learning or the artificial intelligence. So this is kind of it's going to go down under the category of supervised learning and machine learning, artificial intelligence, those kind of problems. It's actually a statistical techniques. So what we wanted to do, we want to identify distinct groups of customers. Say this is an application. They are different in terms of some criteria. So what we want to do, we want to find predictors or variables to identify these distinct type of groups of people or groups of items or whatever it is. So you can have different number of groups, but here for simplicity, we're gonna only solve a problem that has 2 groups here. So suppose that we have 2 type of groups of customers. What we want to do is we want to see based on the customers data that we have, some customers that are likely to subscribe to a certain journal, say Wall Street Journal. So we want to have some predictor or some variables that would tell us whether that person is likely to subscribe to Wall Street Journal or not. That means if that person is likely to be a customer for Wall Street Journal or not. So this is like a two states problem, whether yes or no, whether they would subscribe, they are a customer, or they're not a customer, no, yes, no. So this is like a binary classification problem, what's called. We have two groups, binary classification, 0 or 1. 0, that means they are not a potential customer. Yes, 1 means yes, they are a potential customer. And the predictors or the variables here are the annual income for the customers or the people, and then the size of investment. And that sounds like a good predictors, because people who make more money, they want to, not all of them, but that's a good predictor. And also people who are in the investment market, they want to get updated and follow the news. So that's a good journal to follow for them to subscribe to, the customer to. Okay, so what we want to do now here is we want to find, in a mathematical terms or mathematical formulation language, we want to find actually a line that would identify, distinguish these two groups of people based on these two variables or predictors. So the line is going to have these two variables as its variable, x1 and x2, and then we want to see what should be the line, what should be the parameters of this line, the say the slope of this line, and the starting point of this line, so that it would actually almost perfectly be able to distinguish these two groups of people, so that if we get a new person data, we would be able to predict whether that person would subscribe or not, whether we would classify that person into yes or no groups. Okay, hopefully this explanation has makes sense to you. And then did everyone understand the problem? Any question? All right, great. So let's move on. So what is the goal? We want to find the weights for the predicted variables, or finally the line for predicted variables. So we're going to find weights W1 and W2, so that combined with the predicted variable x1 and x2, and also a certain cutoff point, so that when you plug into this formula of weight multiplied by the predicted variable, for example, W1 multiplied by the income plus W2 multiplied by the investment amount, that's going to give you, when you plug in the income and investment amount, it's going to give you a value. Then you would need a cutoff value, so that if the value that you computed is say less than the cutoff point, you're going to say, okay, no, this person is not a likely customer to subscribe for Wall Street Journal. So you're going to classify that as a 0. And if it's actually bigger than the cutoff point, then you're going to person as 1, or yes, he or she is going to be a potential customer for subscribing to Wall Street Journals. So that's what we want to do. We want to actually come up with this. So Z is the W, the weight, multiplied by X1. So X1 and X2 are our data. W1 and W2 is our decision variable that we want to actually find. Okay, so for certain people, we have data for X1 and X2 for customers, or for potential customers. And then we want to find a W1 and W2, and also the CV, the cutting off value, the cutoff value, so that it would gives us a line, a clear line, a classification line, to be able to classify the person based on income and investment amount into a potential customer, or no, not a potential customer. 0 or 1. Okay, subscriber, non-subscriber. So as you see here, we are looking for W1 and W2. We have the X1 and X2. X1 is the income of the person. X2 is the investment amount of that person. And when you know W1 and W2, it's going to give you a Z for every person. And then you would need a cutoff value so that if this Z that you compute is bigger than that cutoff value, then you're going to say, you're going to classify that person as a potential customer, a subscriber, a class 1, group 1. If the value that you computed Z using this formula is less than the cutoff value, then you're going to classify the person as a non-potential customer or a non-subscriber or a 0 group. Okay, so the decision variable for us in this problem is W1, W2, the weights for income and investment amount, or whatever other in other problems could be different variables here. But here, X1 is the income and X2 is investment amount. So we're looking for W11 and W2 and CV so that it would give us the best classification line, classification output. So what we want to do, we want to maximize, we need to define the objective value. What is the objective? We're going to define the objective as the percent of classification that are correctly predicted. Okay, so maximize the percent of people who are correctly classified by the best set of weights W1 and W2 and the cutoff value. All right, so after we find that W1 and W2 and cutoff value, then for new people that we don't know, just the new people, the potential customers. So we're gonna get their cost. Suppose that you're working for Wall Street Journal and somehow you have access to people's income and investment amount. We have leaked data, probably they know everything about us. So that's a possibility. Our data are being sold on Facebook, on Twitter, on Instagram, all of it. So it's very possible, but they don't want to go with the blind marketing. They want to have like target marketing. So they want to, instead of sending blanket wise ads to everyone, they want to use this classification algorithm to find the potential customers, to invest on them, to advertise them, to target them for advertising. Right? So this is a very interesting problem. So let me open up the Excel file data, which is the WSG, the Wall Street Journal subscriber data, and then I'm gonna share it with you. All right, here it is. I'm gonna share it with you. By the way, if you have a couple of Excel files that they have optimization model open, it could mess up the solver. It could crash. It could actually run a different model. So that's even true for Windows. So for PC. So it could be more true for Mac. I don't know, but that's just a warning that if you have like different models in different Excels and they are all open, and you run one of them, it might actually not work. Okay, so this is just a warning. It's not, may not necessarily be true. So this is the data that we have, the discriminant analysis. This is our decision variable, the weights for income here. So this is W1, this is W2. So I'm going to use the decision variable style here. This is the another decision variable, the cutoff value. So this is also decision variable. I'm gonna also name this. This shouldn't have the label shouldn't have this style. So I'm gonna undo this. So this is, I'm gonna use the naming range here. Same for the cutoff value. All right, and these are the customer data. We have 84 customers or persons. They are not customers, they're potential customers. We have the data for the income. We have so this is X1. This is X2. These are, we have the investment amount. And then we have the actual subscription data. So we have asked them we have gathered 84 people's data, and we have gathered the income and also investment data. And also we have asked them whether they have subscription to Wall Street Journal or not. So for example, this person says, no, it has certain amount of income, certain amount of investment. This person say, no, this person is a subscriber. This person is not a subscriber. So we have the data for the subscription as well. So that's why it's called supervised learning, because we have the data for what we want to make prediction for. Right? So we want to make, based on these data, we want to build a model so that if we get a new person that we don't know whether he or she is a subscriber, and we want to use this model, classification model, to predict whether that person would be interested in subscribing or would not be interested in subscribing. So it's gonna we're gonna make a model here that's gonna, if I give myself, I'm not a subscriber, for example, for Wall Street Journal. So if I give this algorithm my income and my investment amount, the algorithm is going to predict whether I would be interested in some Wall Street Journal subscription or not. So it's going to predict yes or no for me or any of you, right? A new person data, right? So this is our input data. That's why you see it in bluish color here. So now we're going to have to use name range and so on and so forth. So let's do that. So I'm going to use this use range names for all of this. So the 3 column here, the first one is income. It's not the right column, just the top row. So this is going to be income. This is going to be investment. This is going to be actual. I'm going to click OK. So we need to create the Z. Remember the Z value that we have. And Z is going to be W1, which is this one. This is W1. This is W2. And this is X1. And this is X2. So I'm going to compute the Z score here. Score. So the score is going to be the
Did the professor drop off for everyone else?
Yeah.
Yeah, he did.
Yeah, he did.
All right, I had a problem with my internet. Does everyone hear me and see me?
Hi, Professor. We hear and we
Yes,
see
sir.
you. We
Okay.
lost you. We lost you when you started talking about the Z-score.
Okay, great. Let me start over from here. I usually stay at my office because the internet is better there, but All right. So this is how I computed the z-score. We want to compute the z-score using the x1 and x2 data and also the w1 and w2 the weight, and also using the cutting value. So we want to build the model that I show you, z equal to x1. So this is the model. I'm gonna just write it here. Z is w1 multiplied by x1 plus w2 multiplied by x2. And then we're going to decide whether if the z is greater than, say, if it's greater than the cutoff value, then we say we're going to say that person is actually a yes. That means that he's a subscriber. If z otherwise is less than equal to z, CV, then that person we say is not a potential customer. So we're gonna classify it into no groups. Okay? So that's why we have to compute the z value. Okay. So the z value again is W1 income, the coefficient for income multiplied by income plus W2, the coefficient for investment amount multiplied by investment amount. It's going to give us the z score here. I'm going to, I have to use actually these. Absolute value here. So we'll still not for this one. Or so for now works. All right, let's see. Yeah, it works now. Or we could have used the sum product. That would be much easier. Okay. But I just want to show you that this is not magic. So I'm going to also use the range names for z-score. Formula, create names, top row. All right. So now based on the z-score, and also comparing to, I have just given these values, these decision variable random values here. We can start with others, but it has to be created like a certain value, which we don't want to have it 0 here. And then we're going to use this model that we have. Right now we have a model, right? So the cutoff value is 20. Let me make it neater or get rid of the probably 1 decimal points. So right now we have actually a model, and based on this decision value that we have, we can actually make a prediction for. So here I can actually use the prediction. We can say subscriber prediction because we have subscriber actual, subscriber prediction. So now we're gonna say whether this is score, if the score is less than the cutoff value, then yes, otherwise say no. Okay. Subscriber prediction. Okay. So if this value is greater than this value, then say yes, otherwise say no. So because 7.44, which is the z-score for this person, is less than 20, it predicts that this person is not a likely subscriber for WSG. Right? For example, this person is predicted to be a subscriber. And these are our prediction based on the model that we have. If we actually have the actual data for this person, for example, this person, the first person he's not actually a subscriber, doesn't want to be a subscriber, and our prediction say he's not a subscriber, he's not going to be a potential subscriber. For example, this person is actually a subscriber, actually, and our prediction is correct. But this person, we predict that he or she is going to be a subscriber, but actually he or she is not, right? So as you see here, this is going to be our column of prediction. I'm going to also range name this column as well. My computer is again a little bit slow because run out of RAM with the Zoom and PowerPoint and a couple of other programs running with Excel. Okay. No problem. All right. Okay, good. So we have our model, and now we can think about our objective function. What should our objective function be? Our objective function should be the percent of correct prediction. Okay. So before I do that, I want to show you what we want to actually do with this formula, the W1x1, this formula. So what we want to do, we can actually, based on the x1 and x2 values, I can plot these numbers here on a scatter plot, using a scatter plot. So let me give them legends, the axis title. So this is the income for this data. Income. And this is our investment amount. Okay. X1 and X2. And this is how these 84 people would actually look like on this scale up on this graph. We can do something interesting. Which is too large. Can't see everything. Just make it smaller. Up here. Up here. All right. A little bit smaller. All right. So let's actually label these points here with whether they are subscriber or not. Okay. That would be interesting to do. So I'm going to right click on this and say add data label. Do it again. Add data table. Data label. Okay. Comes back and disappears. Value. Here's name. Agent keys. What I want to do, I want all of these points to be labeled by their yes and no. I don't have my mouse with me. It's very hard to work with laptop pad. Value from cell. Okay, good. Value from cell. Now I can select actually this. So I'm gonna ask Excel to show these labels on these points here. And I don't want to use the Y values here. Only yes and no's here. What else do we have? value from cell. It still shows some of the values. It's messed up. It shouldn't show that. Okay. I don't know why it doesn't show that. Okay, now it works. All right, fine. So as you see here, we can actually right now see all of these points, data points of people with yes and no's. And what we want to do is to come up with a line plotted between these groups of people, so that it would distinguish the yes group from no group. It's not going to be perfect. It's not going to be 100% correct. Some of the yeses might actually fall under no groups, and some of the no's may actually end up in the yes group. But what we want to do, we want to find that line, the coordination for that line, so that it would be maximally correct. That means 95%, 84%, whatever amount is possible. We want to find that. Okay. So this is what we want to do. We want to find actually the coordination for that line. Where should it be? Okay, so you can actually draw any line here. It could be one here. So if you, for example, just imagine a line here, it would get most of the yeses above, and the blue one are just no's here, right? So there are infinite number of rows, the lines that you can draw or plot here that would kind of do a prediction or classification for you. But we are looking for the best line. That means a line that would get most of the classification correct. So a line that most of the points above it would be yes values, and most of label, or most of the points below that would be the no labels. Okay, so this is what we want to do. We want to come up with that line. Okay?
Professor, I'm sorry, I missed. Which box did you select to get the yeses and the nos?
Okay, let me do it. I'm gonna show you. For some reason, it just dropped back to. I don't have my monitors with me. I'm just using my laptop. It's very difficult to work with it without the mouse and without monitors. So you click on any of the points here, and then right-click on it. This is in Windows. Then go to Format Data Labels. To format data labels, originally it was picking up X values and Y values. So when you click on the value from cell, okay, value from cell, let me do that again. Right click, add data labels. So it's originally going to label these by X and Y, income and value. Then again, right click on one of these and format data labels. Is going to open up these. Click on the value from cells. It says yes and no. Then I'm going to uncheck the others. So right now it only shows the yes and no's. If you click on it, probably it's going to open up another menu for you, and then you have to select all the yes and no's for that cell, and then uncheck the X and Y. Okay.
Thank you.
Sure. All right. So that's what we want to do. All right. Hopefully this helps for everyone to understand what we want to do. We want to come up with the best line here. Okay. And that line would be W1 and W2 and the cutoff line. So these three, the decision variable would determine the line for us. Okay. All right, so let's now go back to defining the objective function. So the objective function that we want to define is the percentage of prediction correctly predicted. Okay, So let's do that here. I'm going to define it here. I'm going to call it classification matrix. Make it bold here. I'm going to have the prediction here. Not sure that. So prediction is going to be in rows. I'm going to use merge here. And here I'm going to be over, this is going to be a yes group, predicted yes, predicted as no. And here we're going to have our yes and no for the actual. So this is going to be the actual. Okay, I'm going to merge this and make it in middle. All right. So this is going to be our classification matrix. Okay. All right, we are almost. Okay, I think we can cover it. All right, so let's see how we can compute this. Okay. This is where this cell in this matrix is where our prediction was yes, and the actual value was also yes. That means that we have correctly predicted for those people who are subscribers. We have also predicted subscriber. Okay, so how can we find a function for this? You can actually by manually go through this and say this is yes, actual is yes, and prediction yes. So this is one, and then find the next one. Yes here, yes here, yes here, yes here. So what we want to do, we want to actually count the number of all of these yeses in actual value and prediction value. Okay, so we want to find that, but no, we don't want to do it manually. So we want to do kind of like use a function to do that. And to do that, the function is count if with plural. Not, it has two functions, count if and count if z. It has a z for plural. So we're going to use with the plural because we want to have multiple if here, multiple ranges here. So it says criteria. So the criteria here is the actual. I'm going to pick the actual cell here, actual column here. Right. So that's criteria range. What is the criteria? The criteria is yes. So I want to count all the yeses in the actual. Then that's the second range, which is our prediction range. I'm going to select all of these yes and no's in the prediction range. And what I want the criteria to be, I want to count yeses here as well. So what this does is from the actual column and from the prediction column, those that have both yeses is going to count them and it's going to return them here. So right now we have 27 instances or people that both in the actual and prediction column, they are yeses. Okay. So we have to do the same for no's. For no's, that means that the people, the number of instances where the actual what is it? The actual condition is that they have said yes, they are a customer, but our prediction was incorrect and says no. So we want to find those instances. Okay, so I can actually kind of copy this here and then make this correct. So let me go here. So this is where actual is yes and prediction is no. So I'm going to modify this to no. This is where the prediction is no, the actual is no, the prediction is yes. This is where the actual is no, the prediction is no. So this is a very powerful function, as you see here. It can count for you in two different columns the number of incidents with a certain conditions. We can use, right? So if I change the model, this table, this matrix right here is going to automatically be updated with the new predictions and with the new inputs, right? It's gonna look for all of the instances that have, say, yes in both columns, or yes in the actual and no in the prediction. Okay. So let's see here. We want to make sure that our prediction is correct, our model is correct. So I'm going to say here total, and here would be the summation of all of these. That's 84, and that's correct because we have 84 instances. What happened? So we made sure that all of these would have to add up to 84 because we have 84 data instances. All right. Let us take a break, and we're going to come back and continue from here. All right, I'm back. Hope you have got time to take a break. Let's go back to our problem. All right, so where were we? We will try to, we are still building the model. So we want to come up with the objective function here. We develop the classification matrix. The classification matrix is a matrix with the prediction. Is there any question? I can't see anyone. All right. So a classification matrix shows the prediction versus the actual. And what we want to optimize here, I'm going to call it percent. What did I have there? Percent correctly predicted. Maybe I should. Okay. And this is going to be the number of those instances where we predicted yes and actually was yes, plus those instances where we predicted no and it was actually a no, divided by the total number of data that we have. So that's about 82%. I'm going to use the percentage here. This one. This is going to be our output, right? You could actually use, instead of maximizing the percent correctly predicted, you could actually minimize the percent incorrectly predicted, right? Minimizing your mistakes would be equal to maximizing your correct prediction, right? So we don't have to do both, just remove percent incorrectly predicted. So this would be when we predicted no and actually was yes, and when we predicted yes and actually was a no, divided by 84, which is going to be actually the complement of this one. So if you add both, this is going to come up to 100%. So maximizing this is equivalent to minimizing this, right? So, but we can just do one. We don't need to do both. Okay? Right. So that's our percent correctly predicted. That's our objective function. It looks like we have everything. So we can go ahead actually and put this in the solver. Right? So this is what we want to do. We want to change these values, W1, W2, and the cutoff values. These are our decision variable, so that the percent correctly predicted is maximized by changing these values. Of course, based on W1 and W2 and the cutoff value, the score is going to be different, and our prediction based on the score is going to be different, and based on our prediction, the classification metric is going to be different, and based on that, our percent correctly predict is going to be different, right? But remember that in all of these, actually, we actually have used Excel functions, right? So these are not a smooth classical mathematical formulation. We have used Excel functionality here, right? So we can't really use, with this model that we have here, we cannot actually use like simplex algorithm or classical optimization methods, right? So it looks like we are ready. We're going to go ahead and solve this problem using solver. So I'm going to come to solver here. Here is going to be our objective function. We are maximizing this by changing the decision variable, this and this. Not all of it. This, control, and this. Add the constraint. So what are our constraints? All right, what are our constraints? Can anyone think of a constraint? So for example, W1 and W2, they can only be -1 or 1, right? They cannot be, they have to be between -1 and 1, minimum -1, maximum 1, right? So this both should be less than 1, and they both should be greater than or equal to -1. Okay. All right, let's see. Do we have any other criteria? It doesn't look like it. All right. So we don't need actually this because we don't need our variable to be non-negative, because actually W1 and W2 could be on negative. So I'm going to uncheck this, make sure that you uncheck this. This is very important. And then we're going to have to pick our evolutionary approach here as the solution methodology. And I'm going to open up here. The default is 300 seconds, which is 5 minutes. So I'm going to change it to, don't want to wait 5 minutes here for this to be solved. I'm going to change it to 60 seconds, which is 1 minute. And then I'm going to come back to the solver and click solve and see what's going to happen. So right now, the optimal value is 82%. So let's see, by changing these values, W1 and W2, and the cutoff value right now is 20. This W1 is -0.1, W2 is. Did anyone ask any question? W2 is 0.9. So by changing these values, we want to maximize the prediction, 82.1. So if you look at the down below on the left-hand side of your Excel file, it says the incumbent. The incumbent actually is a solution currently working on, which is not optimal. It doesn't know when it's optimal. So right now, the solution that it has found is almost 93%, which is much better than the 82%. And it's trying to find a better one. So just try to solve and solve and solve. Probably it's going to stay at 90, 93 or 94. This solution, the last time I found it was 94. By the way, there are infinite number of lines here. So even if you get the same percent correctly predicted here, say 94%, like say I get 94% and you get 94%, but you could have different W1 and W2 and cutoff values, right? They're infinite numbers. So it asks whether you want to stop or not. It's 92.9, so I'm going to continue. Say if I can get to the 94%. So again, the drawback here is, unlike the classical optimization approach, we don't know the solution that we get is optimal or not. We don't know how good it is. We don't know how far it is from the optimal solution, and we don't know when should we stop, right? So I said, I asked it to continue and not stop at 92.9, because last time I checked, I got actually a better solution, 94%. And there's no guarantee that each time that you run it, you're going to get actually a better one. So this time it couldn't actually get the 94%. I'm going to go ahead and change these values to see if it would actually help. So it's 32%. Let me see if starting from this point would actually help reaching a better one. 91.7. Nope. 92.9. We got this last solution. '94. Yeah, we got to 94. So even changing the original values is going to be important here, as you see here, because it doesn't have, it's not going to go the same way as if you run it multiple times. So you could run this. I could actually run this multiple times and I get different solutions. So I got actually right now is 94%, which is the same solution that I found before. So I'm going to ask it to stop. So 94% is the solution that I found before, and I want it to stop at 94. And these are the values that different from the values that I found before. So before I have found W1 to be negative 0.38 and the W2 is 0.83. Right now, W1 and W2 has negative 0.46 and 1, and the cutoff value here is 5.8, and last time it was 4.66. But the percent correctly predicted is again it's the same, it's 94%. All right, so let's actually go back to our graph that we did. If I can find it, I'm not sure what happened to it. Let me make this small so I can find the graph. All right, see here. Come here. All right, make it bigger. All right, so what I want to do, I want to actually plot this line with the parameter W1 and W1 and W2 and the cutting value. I want to plot the line so that you would see it, okay? So how we can do that? Let me go to the PowerPoint slide so you would see how we can do that. Okay. All right, so we're going to start from here. So your solution likely would be different from mine. There are infinite number of lines that would fit here. So there are infinite number of possibilities here, literally infinite numbers, because it's a line. So there are infinite numbers of W1 and W2 that would get the same z-score value here for us. But when you get to a solution, how you can actually find the line here, or you want to plot the line. So this is how you can do it. The solution is the cutoff value equal to W1 multiplied by X1 plus W2 multiplied by X2. You can actually generate random X1 values, and based on X1 values, you can, using this formula, because you already have W1 and W2 and CV, you can actually find the correspondence X2, and after finding X1 and X2, you can plot that line, right? So for example, using this, if you find two random X1 and X2, say 0, X1 0 and X1 120, that's based on the income. So the minimum income was 30,000, and the maximum income was a little bit more than 100,000. So 0 and 120 would be great, or 110. x1. And for x1, based on this solution, based on this formula, you can actually find x2, right? So say x1, if x1 is 0, then x2 would be CV, which we found it using the model, divided by W2, which we found it using the model, right? So x2 is the cutting value minus W1 x1 divided by W2. Stop sharing. Let's go back to the Excel file. So I'm going to say x1 here, x2. And here I'm going to say the classification line. This is the drawback of using mouse pad, not a real mouse. It's too sensitive. Okay. All right. Okay. So x1 is the income. I'm gonna give it random values, 100 0 and 120, and then I'm gonna find x2 for this x1 value. So this is going to be the cutting value that we have here minus x1 multiplied by w1 divided by w2. The formula that we had in oh, this shouldn't be, this should be negative. The formula that we had in PowerPoint. Okay, good. So we have x1 and x2. This is the formula. I paste it here. All right. So now we can actually add these points into the graph. So look how I can do it. I'm going to right click here and select data. Then I have to move the tables, the graph, so I can see the points here. All right. So right click here, select data, and then when I open up this here, click add here, and then I'm gonna say the class, name it classification line or division line. The x value is going to be x1 and x2, and the y value is going to be x2. Okay. Click OK, and this is the 2 points. This is 0 and whatever value, and this is the 120 and the other way. So now I want to ask Excel to actually build a line between these 2 points. That means that the line that goes from these 2. So I'm going to right click on this right here and then add trend line. Okay, and this is the line. You can actually also ask to put the line here. Okay, so this is the classification line that we built up. So if you look at this, you see that most of the points above this line is yes, are yeses, right? There is a no here. There is another no here. There are some yeses below here, which is our mistake, right? This is our error, classification error. But most of the no's are below this line, and most of yeses are above this line. Did anyone say anything? I can't see anyone. Any question? Yeah, some of you, I think your mic is loose or becomes loose, and then when you talk, just come over here.
Professor, would you mind showing the formula to get the x1 and the x2s again?
All right. Yeah, this is the formula. X2 is equal to the cutting value that we found. This is the cutting value that we found. This is our model of distribution value, right? Cutting value and W1 and W2. So I generated X1 values, just random numbers. And based on this model, you can find X2. So X2 would be cutting value, which is 5.8 minus W1 X1. W1 is here, negative 0.46 multiplied by 0, divided by W2, which is 1. For 0 is 5.85. For 120 is 660.83. I can actually change this to any other numbers. So say 68, right? The line is still going to be the same, right? So the other point is right here. So, we can see. So it's better to go with a value which is large enough to see the other side of the line. So I'm gonna go back to 120. Minus 120. Okay, good. I think we're done here. Yeah,
Thank you, Professor.
Sure. This is, I think this is one of the most interesting problem that we have solved so far. And it's not a classical optimization problem. It's kind of a new hot problem in classification or supervised learning or machine learning or data science, data analytics, all of these buzzwords that's going on. So this is one of the type of those problems. And because we only had two variables here, we had incomes and we had investment amount. So it would be a two-dimensional space, and our model would have to come up with a line that would classify or distinguish these two groups. If you had, say, three decision variable, then we would have a three-dimensional space, and it would no longer be a line, our classification. It would be a plane, right? A two-dimensional plane. And if you had more than three variables, say 4 or 5 or whatever, then we're just gonna call the plane hyperplane in other dimension. We can't really imagine it because we are a three-dimensional species, and we live in a three-dimension probably. So that's why it's very difficult for us to experience it. So that's why we call it hyperplane, no matter what dimension it is. It's going to call it hyperplane. So if you have 4, 5, 40 classes, the distinction or the classification plane is going to be called the hyperplane. All right, any question for this? We are done with this problem too. I'm going to close it. Hopefully I didn't mess up the original file. Let me see. All right, I didn't. Good. So let's go to another lecture. Interesting. To part 3. We're going to solve another problem. Okay. Part 3. So this is another problem. It's forming project teams. say as an instructor, you want to, you actually have a project in your class, and you want to assign or form up teams of a student, groups of 3 or 4, say, or whatever other numbers, and you have a certain number of students, say 25, or it could happen to you. So say at your work, you are a supervisor, you have 25 people working under your management on your other hand, and you want to assign them say 8 projects. So you have to build 8 different teams, and then you have certain criteria. For example, you want to make a balance between the female worker and male worker. So you don't want to have, say, any group that doesn't, it's female only or male only, if it's possible, if you have, you know, that possibility. Or say there are some, based on the expertise of the members, you want to add, say, at least 1 or 2 statistician in each group, or say other criteria, right? So there are some certain criteria that you want to have for these teams. For our example, we assume that we have 25 students, and we want to have 8 to build up 8 teams, so that the teams would get the number of students would be limited, would be between 3 and 4 or something like that. So no more than 4 students per group. You want to have at least 2 or 3, at most 3 males, and also for females as well. You don't want to have more than 1 or less than, say, 3 females for each group or team. And also, say, you have major criteria. So the undergrad course that I teach, and we have a group for it, a group project for it, is the DS412 decision science. It's a decision science major course. So most of the students that take it are decision science majors. So suppose that I want to make sure that each team has at least 1 DS major in it. So that's another criteria that I want to build up the team based on. So what I want to do is, based on these criteria, I want to build these teams so that I would maximize the objective, whatever it is that we're going to define it, for the weakest team based on the criteria that we have. Okay, so each team is going to have an objective value or a score based on these criteria: the number of students, the number of males versus females, the number of these decision science major, or any other criteria. Every team that's going to build up is going to have a score based on that. And then what we want to do is, we're going to find the team with the lowest score, and we want to form the teams so that the lowest score is actually maximized, right? So we want to, it's like upper up the build up the lowest score, the team with the lowest score. So we're not going to focus on the whole population. We're going to focus on the lower limit, the low score team, and then form the group such a way that the team with the lowest score is actually not a bad score, right? So this is a very interesting problem. It's called the max-min problem. We could have also the min-max problem. That means that you are minimizing the maximum. Okay, so this is a maximum problem, or we could have a min-max problem as well. All right, hopefully it makes sense to you. We're gonna look at the Excel, so it will actually make sense hopefully for you. Our decision variables are which student to include in what team, right? So each team should have a student, and each student can only be in one team, right? So Xij equal to 1 means that we're going to assign a student I to team J. If Xij is 1, that means that assign a student I to team J. If Xij is 0, then that means do not assign a student I to group J, to team J, right? So this is a binary problem. All right, so I is the students. It goes from the number of students. So it goes from a student index 1 to student index 2, student index 2, 3, 4, up to 25. And J is the group index. It goes from 1 to 8. Right? So the total possibilities for us is 8 multiplied by 25, which is 200. Right? So there are 200 decision variables, actually, not the possibility. There are 200 decision variables for us. For each student, but for each I, and the summation of xi, j for each I, summing over j, it has to be 1. That means that each student can only be assigned to 1 kid. Okay? So I'm not going to go through the mathematical formulation of this, but this is how it would look like. You know, my mind automatically goes to the mathematical formulation because I'm a mathematical optimization person. All right. So these are our criteria. We want to have 3 to 4 students per team. That means that the size of each team should be less than 3, less than 4, bigger than 3. Okay. So group of 5, not accepted. Group of 2, not accepted. You want to have at least 1 and maximum of 2 male students per group, or we could say female. Okay. And I want to make sure that at least 1 or minimum of 1 and maximum of 2 decision science students are in each team. Okay, so that's another criteria, right? So the goal is based on these criteria. Based on actually another criteria, which is the proposal score of each team. I want to maximize the minimum of the lowest score for the team with the lowest score. Okay, max min problem. Okay, so we have to actually look for the data to make more sense to you. So let me open up if I can get the Excel to open. Interesting codes. I can't get the other Excel to close. I want to open the new one. All right, so let me open up the forming teams. Okay. So let me share this with you. I'm going to save this as so I wouldn't lose the original file. Perfect. Doesn't work. Okay, I'm gonna save it here. No, no. All right, that's great. Sorry, I have a problem with my Excel again. Oh, didn't do it, so I'm not just gonna save it here at all. Let me share it again with you. So this is the data file. You have a student name here on the first column here: Amy, Beth, Kathy, Donna, Ellen, etc., etc. We have 25 students. The other 3 columns shows their other criteria. For example, sex, 0. Say we assign label 0 for female students, assign 1 for male student, or the other way around, doesn't really matter. And the decision science students, if the student is a decision science student, then the DS value for that, it would be 1. Otherwise, it would be 0. For example, Amy is a decision science student, Fred is not. Okay, and then we have the proposal score for each student. Based on based on my evaluation for the project, each person comes up with a proposal for the group project, and then I'm going to, assign them to groups of 3 or 2 or 3, and then the proposal score for that team is going to be, the score of the student in that group, right? So, for example, for Amy, the proposal score is 8. For best is 7. So the minimum value, I think, is 4 or 3. It's actually 3. So for ST, and the maximum is 8. Right? So these are our data. That's why we have the bluish color theme or format, and these are going to be our decision variables. So the decision variables are going to be 8 teams here, and the number of decision variables is 8 multiplied by the number of students, which is 25. So that's going to be 200. All right. So I'm going to drag this down to cover all of the students, actually. Yeah, I don't know what the, yeah, it doesn't work, unfortunately. So I have to, I'm trying to close other programs, but my computer actually has kind of crashed. It doesn't follow my command. Okay, hold on a second. If I can use the Control Alt Delete Task Manager. Task Manager, close the Excel file. Okay, I close it. I'm gonna close Dropbox too. 80% RAM. It's gonna go down to 74. I'm gonna also close some other application. Do I need the PowerPoint? I don't need the PowerPoint, so I'm gonna close that one too. Okay, good. So now I have more RAM. Hopefully this time it works. Oh. Save it as 3 rows. So, all right, let me share this with you. I think it's working this time. All right. Hopefully my Zoom is working. Does anyone hear me?
I hear you.
All right, so I'm gonna drag all of this decision variable down. So it's going to be a total of 200 actually values here. 0 here means that Amy is not in team 1. 0 here, it means Amy is not in team 2. Is not in team 3 or 4 or 5 or 6 or 7 or 8. But we want to make sure that Amy is actually in one group. So this is what we're going to call it, assigned to a group. So I'm going to sum up all these values for Amy. And this has to be equal to 1, actually. So I'm going to call this required. The required value is actually 1. And it's not a decision variable, it's actually an input. And I'm going to make this center, and then I'm going to drag it down. Oh, this has to be 1 and 1 and 1. Right, good. So this is one condition. the condition is that every student has to be in exactly one team. Okay, so this is gonna do it. This is the condition, the constraint that's gonna do it. And we need to add the other constraints. So the other constraints is that we have to make sure that the mail criteria, the DS science, decision science criteria, the number of people per team criteria are all met. Okay, so mean size. Mean size, this is the size of the group. Max size. So the mean size is actually 3. The max size is 4. And I want this to be less than equal to greater than equal to the mean, less than equal to the max. Okay. So we want to, okay. And the values under each team is going to be the summation of the number of people that are in that group. So for example, for team 1, it's going to be the summation of all of these values. Okay, so right now it's 0. I can drag it down here. Okay. So this is for all teams. So say example, if I add Amy to team 1, if I add Kathy to team 1, these are either 0 or 1. If I add Ellen to team 3, if I add Hank to team 4, if I add Carl to team 5, if I add, say, Mary also to team 5, and Oprah also to team 5, and some other actually values here. So I shouldn't add any student into 2 teams, just 1 team. So this is not a feasible solution, but it's just a solution. So as you see here, I want to make sure that the number of the member size, the number of member teams, the number of members for each team is greater than 3, the minimum, and is less than 4, which is the maximum. Okay. So this is the team size constraint. And I'm going to make this center. Okay, great. I'm gonna copy this. Copy actually this down here. Copy this down here. And here I'm gonna call this the other criteria. So that was the number of males. So this would be the mean number of males, and this would be the max number of male students or female students. Okay, the mean and max was 1 and 2. So we don't want more than 2 male students in each team and at least 1 male student in each team. So I'm gonna call this the male number of male constraint. Male student constraint. And I'm going to merge this in the center. You also need the decision science constraint. So I'm going to copy this here. This would be the mean DS, the mean number of decision sciences students, and the maximum decision sciences students. Mean max DS. Okay. The minimum was 1 and the maximum was 2. So this is okay. I'm going to write here the number of DS students. Gonna merge this cell. All right. We didn't do this, so we have to also do this. So here we want to make sure that the number of male student in team 1 and team 2 and team 3, team 4 and 5 and 6 and 7 and 8 are between mean value and max value. How we can do that? So what we have to do is for each student we find the sex of a student. For example, this is the mean number of males. If it's 1, then it has to be counted. Okay. So this would be the sum product of team 1 and sex. Okay. Right. And instead of this E4 to E28, I'm gonna use sex here. Oh, I haven't actually named this. So let me go ahead and do that. Okay, I'm going to use range names for these 3 values, the 3 columns. Range names, top row. Okay, so now it looks better. So this is the sex column and the T1 column. But I haven't given the T1 name, so now I can actually drag this up to the team 8 and it's gonna do it. It's gonna work on. So this worked actually. I'm gonna centralize it. Okay. So it says that there is 1 male student in group in team 8. Okay. So let's add actually another one. Yogi is also male student. So if I click 1 here, this number should change to 2. And it did. Okay. I shouldn't add any more male students because this has to be less than 2. So this is an infeasible solution right now, but we're not gonna care right now. We're gonna expect the solver to take care of this. Okay. All right. So for the number of DS sciences, we're gonna do the same. So this is going to be the sum product of the DS and T1. Okay. So it says there is one student. There is one student who is decision science major in team 1. Okay. So because the T1 is not named, it says E4 to E28. So that's actually dynamic. I can actually drag this to team 8. So it would actually cover all of this. It would compute this for all of this, right? So for example, team 5 have 2 student decision science major. Team 4 doesn't have any DS student major, so it's infeasible. It has to be between 1 and 2. Okay? So this is for this constraint. What else do we need? We actually need to find the score for proposal score. Okay? So let's find the proposal score. Proposal score, I'm going to give it here. The mean proposal score, the mean proposal score. Okay. Let me actually put this here. Here, I'm gonna compute it. So this is going to be the sum product of score and team one. Okay. Now I can drag this down. It's crazy. 120. This is stupid. Okay. It didn't get the other index. This is the downside of working with mouse pad instead of real mouse that I have used to. Okay, T1, I can grab this. Okay, T3. So I want to pick this one up to this value. Okay. All right, this time it works. So I can drag it down up to here. Centralize them, and this is going to be the minimum of these values. Okay, so the team with the minimum score, proposal score, I want it to be maximized. Okay, so this is our output. I'm gonna use the output format here. This is output format. Right now is 0, which is crazy because there is no one actually assigned to this team. So I'm gonna assign student to this team. Not this one. No. Okay. So right now is 5. Okay. This is actually not a feasible solution, but we can. I'm gonna go ahead and assign range names for this. Let's quickly go to see what range name you have. I have DS, score, and sex. I'm going to also name the assigned group, the assigned column, and also the required column for making the modeling simple. Right. Top row, I'm gonna have to do it individually. Oh. No. All right, I named that one too. I'm gonna name this one and 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 this one. Top row, I'm gonna name the output, right column. I'm also going to name these. Top row, I'm gonna name this top row. I'm gonna also name this top row. Okay. I think we are almost done. Assign DS, max DS, max minus, max size, max DS, min DS, min size, number of decision size, student number of men, student required score, sex, and team size. So it looks like we are almost done. And we are ready for modeling. Right? So right now, the team that I have assigned, first of all, this assignment is not correct because it's not feasible. For example, Amy is not in any team. Beth is not in any team. Our team size is violated because we have teams with less than 3 members. We have teams with 0 males. So this constraint is also violated. This constraint is also violated. So let's go ahead and actually try to solve this problem. Our objective value is here. we want to maximize this. This is the minimum of the score. We want to maximize this. And our decision variables are these values here. I can get it. I can actually name this decision variable. So let me go ahead. Before I do that, I'm gonna go ahead and name this. Name all of this as assignment decision. Now it's better. So assignment decisions, great. Now I'm gonna add the constraints. The constraints, I want the assigns to be exactly equal to these values, which is 1. Add. The other constraint is I want these values to be binary. Add. The other constraint is I want the team size to be less than its maximum and be greater than its minimum. Also, for the number of male students, I want it to be less than its maximum and greater than its minimum. I also want the number of these students to be less than 2 and greater than 1. Okay. So maximizing the mean proposal score for the assignment decisions such that the name didn't go through. It should go through. I'm not sure why it didn't go through. Probably if I open it. Okay, let's see. This is, where is it? Formula, name decision, team size. Team size. Well, didn't get it, but it's fine. Okay, let's go back to the solver. So we have all the constraints. We don't need non-negatively constraint. It can be 0, 1. It's binary, so it doesn't matter actually. Non-negative. And then I'm gonna go to the solver, evolutionary solver. I'm gonna be let it run to 120. That's 2 minutes. Let's go to 30 seconds. Get the solution faster. So right now the mean proposal is 5, and actually, first of all, our solution is not feasible. So let it run to see what's going to happen. So the incumbent is 11, and that's for a feasible solution. Well, the median score that I found is 18, so we have a way to go. And one more thing, your initial solution is important. So this random solution that I found here is the reason that I got not a good score. It's 11. Okay? Before that, I had actually found 18. Okay, so but at least the solution that I got right now is feasible. So it makes sure that each student is assigned to exactly one team. It makes sure that the team size constraint is met. So all of the teams are the size are between 3 and 4. It made sure that at least one male student and at most 2 male students are in each team, and it makes sure that at least one decision major student, and at most 2 decision major students are in the group. And the minimum score for the minimum proposal score for each team is actually 11. Okay, but we could actually change it. So let me go ahead and try this again. But I wanted to start from another solution. So this is just all zeros. And I'm going to run it again for exactly the same 30 seconds. And I wanted to go to 0% optimality. So let's see what's going to happen. So you can see the sub problem in common. Actually, it went to 16. So we beat our last solution. 17. And hopefully it's going to go to 18 that I found. Oh, it got to 18. You could get easily different solution because this problem has many different solutions. I'm going to ask it to stop. So this is a solution that is feasible, and the minimum number of the minimum proposal, as you can see here, is actually 18. So we have teams with all of the criteria are met. We have made sure that each student is exactly in one team. We have made sure that the team size is between 3 and 4. We have made sure that at least 1 and at most 2 male students are in each group. We have made sure that the number of BSS students in each group is between 1 and 2. And the mean proposal score is 18, as you see here. So we have teams of 25 score and teams of 18, 19, right? We could actually do, that would be not serve the purpose. You don't want to minimize the maximum, but you could find the maximum score, proposal score here, and minimize, right? So this is like a min-max maximum problem, right? So anyway, we actually solved this problem. This is a fantastic problem. It's a strange problem. It's not similar to any other problem that we have solved before. It uses kind of non-smoothing, non-continuous, non-typical or atypical kind of problem and formulation. But we were able to solve it using the evolutionary solver. And we are not sure if we found the optimal solution, but we got actually a feasible solution and a good solution, right? And that's important because if you just go ahead and try to play with this, just coming up with a feasible solution is going to take more time than coming up with this solution. So in less than 30 seconds, actually, this evolutionary approach solved this solution. It found a team assignment with a minimum score of 18. So if you would try to do it, you would understand that how difficult this problem actually is. Okay. All right, so I'm gonna go ahead and stop share this, and I'm gonna close this. Don't save. I'm gonna go back to our PowerPoint. All right, so we're over here. So we did that. All right, so what we had. How balanced is the optimal solution? It looks pretty balanced. We had teams of 18, a couple of 18s, 19, 20. We had 125. We could do sensitivity analysis, for example, with the maximum number of males ranges from 2 to 4, with the DS student, with the proposal score. So we could do we could actually run the solver table, but remember that it's not like the problem that we solved before. It's gonna take time each time that you run it. So you might actually get a longer solution time if you want to do sensitivity analysis. Okay, so that means that if say you have 10 scenarios, it's gonna run for 10 multiplied by 30 seconds, which is 300 seconds, which is 5 minutes. Okay, so it's gonna take time, but you can actually do it anyway. So one more interesting, or one more not interesting, actually, the opposite of interesting. One sad thing about these solver approach is the evolution solver is you can actually easily get to the limitation of Excel, the size limitation. So that's something to be aware of. But there are the professional actually softwares available to do that, but you have to pay for them. For example, the solver that I use, it's not a solver. It actually is a professional mathematical optimization solver. It's called Groovy. There is also Cplex, but they have licenses for academia. You can actually get that for free. And but if you are working for any organization or a business, it's non-profit organization, you have to pay. You have to actually the organization have to pay for it to get the license. Anyway, so that's about it. I'm actually, we have enough time. I can show you my type of research later after we are done with this lecture. The evolutionary solver expands the type of optimization that we have been able to solve so far. As you see here, it's a different class of optimization that we have so far. It is very cool. I believe it's very cool. It's very strange kind of modeling. It just another class of optimization that makes us more powerful in this domain for the decision making. For this continuous non-smoothing, we use the some functionality of Excel, which would help us actually in modeling, such as index, the all different constraints, the if, the count if, the mean, etc., etc. Right? So we use these functions from Excel that are not mathematically, like not classical mathematical formulation that we have used in Simplex or in linear programming or mixed integer programming. But nonetheless, using the evolutionary solver, we were able to overcome these functions and use solver to find a good solution. Not necessarily the best solution, but a good solution. Right, so we are done actually with the lecture. Any question? No question? I'm going to show you one of the research that I've worked on. Let me share this video. So you might be interested to know what a real practical problem look like. Okay, so this is a paper that I have been working on. I have submitted to the International Journal of Production Research, and I got the review back. I'm currently trying to revise it and just submit it for publication. If I can get the board to Microsoft Word doesn't work for me. Okay, let me show you the model, the mathematical model. All right, so this is the mathematical model. All right, so this is a supply chain management problem. It's specifically semiconductor supply chain management. We are trying to maximize the profit. We have got like a case study data. This is a stochastic programming, so the data that we have is with uncertainty. And we are using like the distribution of the random variables and with the stochastic programming with the scenario tree generation here that you can see. And to be able to solve this problem, there are, based on this is just a mathematical model. So based on the problem that you have, the number of variables and constraints can actually grow dramatically and exponentially. For example, this is the data that I have. This is like a case study that I've worked on from two companies in Silicon Valley, and I can't show you the solution. I'm going to show you also the software that I'm using. So when I run it, this is not like the case study is not too large problem. It's just a medium-sized problem, or small to medium. And it generates more than 10 million variables. Okay, that's crazy. Okay, that's not, again, that's not like a too large problem, and it generates more than 10 million variables. So, you know, Excel is just way beyond the shoulder of Excel. It can't even do a million, let alone 10 million. I think it's, I can't remember, but it's like, it could be a couple of thousand variables, 12,000 or something like that. Like a couple of thousand variables, the number of variables is the maximum size that Excel can solve. You know, so the number of constraints also matter. So let me go ahead and show you how we can model this, solve this. So I use Python as the programming language because, yeah, that's true that Excel can be a pain, but it's also very user-friendly, easy to model a problem. To, you know, you can see everything. It's very easy. It's very easy. But in real application, you have to use programming languages. So I use Python, and then a Groovy API for Python. So I have to make the mathematical model, then read the data from a file, and then upload the data, input the data into the model, then use create all the decision variable, create all the objective function, add the constraints, and then ask solver, yeah, Groovy form, which is to solve the problem. So let me actually show you what I have here. Oh, it says it crashed. I know it crashed. Last time I want to go to Anaconda. Okay, I think it's gonna run. So I'm using the Spider application in Anaconda, which is like an IDE or a platform for Python. I'm trying to load that because I code using Spider and Anaconda. Trying to load it. All right, I think we're there. Okay. Well, the files are not there. I have to open it. So let me actually share it with you. Hopefully it looks interesting to you. I don't know. I'm just trying to show you a real application of the thing that we have learned here. What does it say? So this is the Spider. This is where you write your code. This is the interactive part that you can actually write codes and get. I am a little tired. Okay, so it turns out this, but you can write like 1,000 lines of code here and then ask it to run it. So right now I want to open the file for my paper. Codes. All right. Okay, now I got it. So let me share this again with you. So this is, I have two files here. The first one is the data. So I generate all the data, the C numbers, all the parameters here. Then I have to create the scenarios here, etc., etc. So this is the file. Then this is the modeling file. So I'm going to import the GroovyPy, which is the API application for Python from Groovy in Python. It's gonna get it in Python, so you can actually write the code here. I generate all the variables here. All of them are binary integer variables. And then, as you see here, there are a lot of them. And then I'm going to add the constraints here using this is the name of the model. Add constr is adding constraint, and then the constraints that's going to add it. So as you see here, I have to code everything. Like, it's not like Excel that's super friendly. You just write some numbers here and add if and for and what, it's very easy in Excel to do that. But also Excel is not as powerful as this. This is the real thing, right? This is the thing that everyone uses in the industry, and this is the thing that if you want to work in this area, you have to use too. So as you see here, a lot of codes, more than 400 line of codes in this file. And finally, I ask you to run it. So this is I say, okay, optimize my model. And then this is just to extract the solution here. So again, as I said, it has more than 10 million variables and some million constraints as well. So it's a huge problem. Okay. All right. So hopefully you enjoyed it. I'm not sure, but I just want you to see a real application. Thank you very much, everyone. I really enjoyed this session, like the other sessions. Hopefully you have enjoyed it too. See you next week. Have a great night.
Thank you for showing us your Python project, Professor.
Have a good week, Professor.
Thank you,
Have a good night,
Professor.
Professor.
Thank you, Professor.